So, welcome to the first lecture of Remi Coulon. And he'll be talking about twisted Patterson-Sullivan measures and applications to growth problems. All yours, Remi. Yeah.
Thank you very much. Well, thank you very much for a series of lectures. So I'm not maybe the best at following both my presentation and the chat and everything. So
yeah,
don't hesitate to interrupt me. There are some questions in the chat, or just ask a question directly on the way. That's even better. So yeah, really do not hesitate to stop me and ask questions if something is too complicated or too slow or whatever. I'll adapt myself to your pace. Okay, so let's begin. So here is the general context of the topics I want to speak about. So you start with a group which acts properly by isometry on any nice space. And the idea that you'd like to measure what is the size, let's say, roughly speaking, of its orbits. So one way to do that is to define what's called the exponential growth rate. So basically, you look at all the elements here that will hardly move a point x, and you count how many of them there are. So you can how many elements you have in a given ball for the metric which comes from the metric of x. And then this gives you a finite number because the action is proper. And you try to understand what is the asymptotic behavior of this number when the radius of the balls goes to infinity. And to quantify this asymptotic behavior, well, the standard thing is you take the logarithm, you divide by r, and you take the limit as r goes to infinity. So roughly speaking, it means that if you look at, oops, that's not the right tool. If you look at the cardinals, let's say, of the ball of radius r, roughly speaking, they should behave something like e to the exponential growth rate times r. That's, well, maybe there are some multiplicative constants here and there, but that's sort of the meaning of this asymptotic behavior. And then, well, that's an easy exercise here to check that it will not depend on the point x, just triangle inequality. But it does depend on the space x, but most of the time the space x will be kind of obvious from the context. So I may write here hg like this instead of hgx if there is no ambiguity. So now let's have a few examples here first. What is this number? Well, let's start with some basics. So take the group which is just z squared. So usual, action on grid. Sorry, my drawing is not super nice. And then, well, the cardinality of the balls here grows quadratically. That's the standard exercise. So when you compute the exponential behavior of this thing, what you get is that the exponential growth rate will be 0. So on the other extreme, you can look at the group G, which is the free group of rank R, which acts on a calligraph, which is here, let's say, a tree. So you probably noticed the standard picture of the calligraph of F2, something like that. And then the growth of the balls this time is exponential, and you can make the computation and check that this exponential growth rate is exactly log of 2r minus 1, if r is the rank of the group. So now, let's start with a very basic remark that if you take a subgroup H of G, you can measure the growth rate of H and the growth rate of G. And of course, H is smaller than G. It's a subgroup. So the growth rate has to be smaller than the one of G. And the question I would like to ask during these lectures and try to answer is, what are the possible values for the growth rate of H as H run over all the subgroups of G? And more precisely, what are the extremal value of this kind of growth spectrum? So especially, when can we have the growth rate of H equals the growth rate of G? So a necessary obvious condition, sorry, not necessarily a sufficient obvious condition is to ask that the index of H in G is finite. In this case, you have equality. But can we have more? So here's a first statement. We'll elaborate on this later, which sort of answers this question. So you start with the group G, which is acting properly, co-compactly by isometries on a hyperbolic space. So hyperbolic here means in the sense of Gromov. And you consider a normal subgroup N of G. Then you can exactly answer the question, when do we have equality? So we have equality between the exponential growth rate of N and G if and only if the quotient is amenable. So I will not define amenable yet. Probably you already have some definition. I'll give my preferred definition later, but if you want some example just to keep in mind, any abelian group or even nilpotent group or even solvable groups are amenable, or groups which are sub-exponentially growing are also exponential examples of amenable groups. So one way you can think of amenable, that's the way I will think in this lecture, is that's kind of a small group. And then the philosophy of the statement is, if your normal subgroup N is as large as possible, and here by large, I measure the size with the exponential growth rate. So if it has a maximal possible exponential growth rate, then the quotient has to be small, here in the sense that the quotient has to be amenable. So this statement that I gave you is the last step of a long history of results in this direction. So I would like to mention a few of them. So the first one here goes back to the 80s. So independently, Grigorchuk and Cohen proved the statement when G is a free group using some kind of brute force counting, let's say. Then you have another statement which deals with fundamental groups of hyperbolic manifolds that was proved by Brooks using spectral theory of the Laplace operator on a manifold. And then you have a long list of people, probably I forgot some of them, I'm sorry about that, which try to improve the statement, most of the time in this context of the following group of a manifold with, let's say, pinch negative curvature, to make it very vague. So here's my plan for this series of lecture. So first, well, I will briefly go through the proof, or possible proof, for the free group using more coding and operators, because that will be, I guess, a safe place to start introducing a strategy which consists in twisting certain operators. So that's, I think, a good way to start. And then we'll move on to a more general setting, which can be used to prove this statement, where at the end we need to consider measures that we will twist by some representation. So this is kind of very weird measure that will take place in, that would take values in binary spaces. So since those measures are pretty weird at first sight, I thought it would be easier to start with operators, because twisting operators is more I don't want to say safe, but it's easier to accept at first. So to do that, let's start with the free group. So, oh yeah, maybe I should first make a remark about the statement. So there are two directions in this statement. So you have two properties. The first one is you have two numbers, the exponential growth rate, which are equal. And the second one, you have a quotient group, which is amenable. So if you try to think a bit, what is a priori which assertion carry the more data? So you can think two numbers are equal is a very weak information. On the other hand, saying that a quotient is amenable, it's a very rich information. So if you think in this way, a priori, there is an easier direction. So if you go from amenability to the equality of growth rate, that's supposed to be the easy direction. But we'll see that sometimes it's not that easy, but it's supposed to be the easy direction. On the other hand, if you only have the information that two numbers are equal, and you want to deduce that a certain quotient is amenable, that's a much harder problem. And then the hard direction. So we will start with the free group, and I will explain you how the hard direction goes in the free group. I don't want to do the easy one because we will see a much nicer, let's say, approach to cover the easy direction in a very dual situation later. Any questions so far before I start the case of free groups? Again,
Remi?
Yes.
Last year we learned that any result about a normal subgroup should be extended to invariant random subgroup. So so it's not the last step in the long story.
Yeah, sure. Well, the thing, yeah. So I tried to be pedagogical, and I actually did not give you yet the full statement, because I studied here for normal subgroup, but we will see maybe tomorrow or on Wednesday that there is an analog statement for any subgroup.
Yeah.
And indeed, we could then move to invariant normal subgroup.
Okay, thank you.
That's probably some stuff that which is possible. Yeah. Yeah, I guess saying it's a bit the end of the story is a bit probably also me bragging to say that the statement is the best you can get. Any other question? Okay, so let's move to the case of free groups. So first, I want to say a few words about Keston criterions for amenability. So something you may have heard, because somehow this statement, so equality of exponential growth rate gives you amenability, is very much an analog of the Keston criterion in slightly different settings. So what is Keston's criterion? So you fix a subset S, which is a symmetric generating set of G. So typically you take a free basis of the free group, and you take the generators and their inverses. And then you consider the uniform probability measure on this subset S and start a random walk. So either you can think a random walk on the quotient group, or you can already start the random walk in the group G. And then you may ask, what is the spectral radius of the random walk? So asymptotically, what is the probability that after n step you come back to the identity, if you think in the quotient group? Or here I'm thinking in the group G, so I'm looking at the probability that here after n step, oops, I want something bigger, that after n step, I come back to the normal subgroup n. So that gives you some number between 0 and 1. And Keston amenability criterion tells you that the quotient G mod n is amenable if and only if that spectral radius is 1. So why do I say it's very similar to that other results of Cohen-Grigorchuk? Well, if you think a bit, so what is this probability measure that after n step, you come back to the identity? Well, you look at two stuff. So on one hand, you count all the words over your alphabet S, which have length n, and such that the element of the group that they represent belongs to the normal subgroup, n. And you compare just to the number of all words on your alphabet n, or S, sorry, whose length is n. So that's the probability measure that after n steps goes back to the identity. So this is what the kind of thing you consider when you look at question criterion. But now if you think, what are we looking for when we compute the growth rate of G? Well, basically, it's not exactly equal because there is some limit, etc. But what you're interested in is looking at all the words over S, which now are reduced in the sense that there is no letter which is followed directly by its inverse. And same, the length is n, and the element, sorry, that's, I made a mistake here. This is hn. If I want to compute hn, then I look at all the words which are reduced of length n and which belong to the normal subgroup n. And you compare this to the growth rate of the group G itself, which is just asymptotically the number of elements which are, again, reduced and whose length is n. So the only difference between sort of two approaches is for random walks, you consider all possible words, and for exponential growth rate, you consider only reduced word. So the original proof by Cohen and Grigorchuk, for me, is kind of not very natural in the sense that what they did is they tried to relate those two numbers, hn and hg, the two exponential growth rate, to the spectral radius of the random walk. And they can write, because the free group is somehow very symmetric, all the generators play the same role in the spectral radius of the random walk and those two exponential growth rates. And they get that if hn equals hg, then the spectral radius has to be 1, therefore the quotient has to be amenable. But let me tell you why I think this is not very natural. Because somehow, if you think, well, maybe a disclaimer, I'm absolutely not, my primary field is absolutely not a dynamical system. So I may say some very terrible thing about dynamical system, but here's the way I think. So I view a dynamical system just a counting device for the moment. And depending on the kind of stuff you want to count, you will choose one or another dynamical system. So in the first setting, the Keston criterion, we are just trying to count all possible words. Eventually, those words may have cancellation. We don't care. And for that type of counting, then the natural dynamical system to consider are random walks. But now for the second problem, the Cohen-Grigorchuk statement, we try to count only reduced word. So it's not very natural to consider random walks or to reduce the theorem to random walks. It would be much more appropriate to consider another dynamical system, which here turns out to be the geodesic flow, that will count only reduced word. And then try to see whether the same kind of proofs you can run for the Keston criterion will work for that other dynamical system. So this is what I want to do now. Okay, so but before I start, maybe I should give you what is my favorite, well, what is this appropriate definition, let's say, of amenability in this setting, or for my purpose, because there are plenty of definition of amenability. I'm sure each of you has his favorite definition, but here's the one I'm going to consider. So let me first write down some vocabularies. So I consider a representation, a unitary representation for group G into a certain Hilbert space H. So that would be a unitary representation. And now fix a finite subset S of the group G and some epsilon positive. And I will say now that a vector in H is called S epsilon invariant if for every element S in that set, if you look at the norm of rho of S phi minus phi, this is strictly smaller than epsilon, the norm of phi. Oops, almost at the end. So basically, I want a vector which is hardly moved by any element in my finite set. So note here that the inequality here is strict, so that I don't have to assume that phi is a non-zero vector. And then the next definition, next vocabulary will say, I would say that rho almost has invariant vectors if for every S in G finite, for every epsilon positive, there exists a certain vector in my Hilbert space, which is S epsilon invariant. So now, among all possible unitary representation, you can consider a regular one. So imagine now n is, oops, that's very bad. So imagine n is a normal subgroup of G, and then you can consider the Hilbert space, which are just the square summable function of G mod n. And so G acts by translation on the quotient. So that gives you a certain unitary representation from G into H. So basically, if you compute rho of G applied to a vector phi, so phi is a function from G mod n to, that is the real numbers. So if you compute what is the value of this function at a certain point x, that would be, I hope I'm not mistaken with the inverse phi of G inverse x, something like that. So that's a possible unitary representation. And now the definition of amenability we will use here is that G mod n is amenable if rho almost has invariant vectors. So the reason why I like this definition is because we'll see next time that it's generalizes very easily to situation where the subgroup N is normal or normal subgroup. So that was something would be nice. And also, if property T, that's a good framework to work with. If you're more familiar, for instance, with the definition which involves Fermi set, when for every epsilon, for every S, we have a set in the group G, which is basically hardly displaced by the generators, then you can make the connection with this this definition. So the almost invariant vectors of your representation here will be exactly the characteristic function of your Fermi sets. Typically, that's the correspondence between those two definitions. Okay. Any questions so far? Well, if not, let's start to the proof in the case of the free group. And I tell you, I will use a point of view which is not the one I will follow in the next lectures, but that will sort of motivate the kind of construction we will do later. So remember, what I will only focus on the so-called hard direction. So I want to prove that if the growth rate of N equals the growth rate of G, then that's my goal. G mod N is amenable. And what I'm going to consider is a certain dynamical system that I will represent here with a finite state automaton. So how this goes? So imagine you have 4 states. So, well, I will work here with a free group which are generated by 2 elements, say A and B. So we have 4 states which correspond to the generators, let's say A, B, and their inverse, B inverse, A inverse. And I'm going to add edges so that if I follow a path in this graph, I will read reduced word. So what I need to do if I want to do that is connect all possible states together except a letter and its inverse. So that's why I put them on the diagonal so that there shouldn't be no arrows along the diagonal. So if I've done that, I'm almost done. I need also to add an arrow from A to itself, B to itself, etc. So imagine now you have this graph that's kind of a machine, and you can start anywhere you want and start following a path in the directed graph, and you get a word which is the one you obtain when you concatenate the letters you see on each state. And it has been designed in such a way that any word you can read on this graph is a reduced word. So if you know stuff about subsheet of finite types, you can consider all the infinite words, all the infinite reduced word, and you will consider the shift operator on this kind of thing. Basically, it's a baby version of that. So if you don't know that stuff, don't worry, I will not use it at all. So now, associated to this graph, I can write an adjacency matrix. So basically, I have a 4x4 matrix. So the entries are the labels of my states. So A inverse, AB, A inverse, B inverse, and same on the rows, A, B, A inverse, B inverse. And I will put a 1 every time there is an arrow from A to well, from one generator to the other generator. So it looks like this: 1, 1, 0, 1, because there is no arrows from A to A inverse, but all the other transitions are allowed. So here 1, 1, 1, 0, if I'm not mistaken, 0, sorry, 1, 1, 1, 1, 0, 1, 1. So that's the adjacency matrix A. And it's a standard exercise. If you compute the nth power of A, so if you compute the nth power, you will have something which is let's call it Cij matrix. So the number Cij will be exactly the number of paths that go from the state I to the state j. So if you want to compute how many reduced words of length n you have, well, basically you compute the nth power, and then the asymptotic behavior of the coefficients will give you that number. So if you try to reformulate, what you will see is that if you compute the spectral radius, well, here actually it's just the largest eigenvalue of this matrix. Well, it's 3. It's easy to see that 1, 1, 1, 1 is the eigenvector for this eigenvalue. And this 3 here is exactly exponential h of g. Remember, the growth rate of the free group is log 3. It's not a coincidence, that's just the way it is designed. We are just counting here reduced word of length n with this matrix, and asymptotically, the largest eigenvalue will give you the asymptotic behavior of a number of words like that. Okay, so before I move on, I will just reformulate that matrix A in a slightly different way, but that will be helpful right after. So A, that's a 4x4 matrix, so I think it acts on R4. But I will see R4 now as R indexed by, well, R to the power the generator set, so which you can think of as all function from S to R. And now if I rewrite the matrix multiplication, this operation of applying the matrix, how does it go? So imagine you have a function from S to R, just a weird way to write a vector in R4. So A of u, what is it? So I want to compute A of u at a certain generator X. So if you write and then matrix, basically you're summing over generators Y, u of y, but not all the generators, the ones such that ux is different from 1. You never have an arrow in the graph, in the previous graph, you never have an arrow from one element to its inverse. So when you look at the coefficient that you are summing, we always avoid the inverse of the element we're involved here. So especially if you iterate, I think there is a very nice formula that you can prove by induction. If you compute a to the n applied to u, and what is the value on the generator x, that will be the sum over all words which are reduced of the form ux is start by x, y1, etc., yn. So those words are reduced. And now you sum u of yn, the last letter of your words. I hope I'm not mistaken. I checked the computation yesterday. I think it's correct. So that's another way to rewrite this operator. So what does this operator A does? It's just a way to count how many words, reduced words of length n do you have. But it does absolutely not follow, if you follow a path in this graph, you will get a word, but you are not following what is this path in the group G or in the quotient n. We're losing that data. So what we'll try to do now is to twist that operator in such a way that we will keep track not only of this counting process, but where do these reduced words go in the group G or in the quotient G mod n. So how does it go? So let's fix now a normal subgroup of G. And again, I'll consider the Hilbert space, which is L2 of G mod n, so the square summable function on G mod n. And associated to that, we have a unitary representation from G to U of H. So here I've seen, maybe I can write with a different color. Here I have seen A as an operator on certain function from S to R. And well, it would be suitable here to take L1 function. The space is finite dimensional, so I can take any norm I want on this space. I will not change anything. Now, what I'm going to do is I'm going to consider the space of L1 function from S, but instead of taking its value in R, it will take its value in this Hilbert space L2 of G mod n. So basically, it's h to the 4. And now I will consider a certain new operator, which I wrote A rho, which will be a bounded operator acting on this space. So it's basically the same kind of operator as A, but there is a twist that will incorporate that representation. And this representation rho is exactly the ingredient which allow me to follow what is the trajectory of my words in the group G mod n. So let me give you the formula here. You will see it's very analogous to the formula. I have some trouble with my. It's very analogous to this formula. Well, I can write it like that. Oops. So the formula for A rho is the following. So I take phi, so in that space L1 SH. So remember that a function from S to the Hilbert space S, H. So if I apply A rho to phi, that's a function from S to H. So I want to compute what is the value of this function at a generator S. So this is something in S. So basically, I just copy the same formula as previously. So I sum over all the generators which are not the inverse. Oops, maybe you cannot read correctly. Not the inverse of X. I want to sum phi of Y, so the function phi computed at the generator S, but I had a twist here, which is a twist by the representation rho. So in this way, it's not very difficult to observe that you get an operator, a bounded operator on the space L1 of here L1 of S of H. So, and more generally, you can compute what is the nth power of this new operator. oops, I should probably add some, how do I do that? Does this work? Yes. So let me compute for you the nth power of this operator. So you get the same kind of formula. So if you compute the nth power of a rho applied to phi, so again, that's a function from S to H. So if I compute that at a generator X in S, you will get the sum over all words X, Y1, Yn, which are reduced. Sorry, my handwriting is very bad. And then you twist with rho applied to Y1 to Yn times phi of Yn. So I said this operator is supposed to keep track of the trajectories of the word, of the radius word in the free group. It keeps track of their trajectory in the quotient group. So how do we see that? Well, here's my first claim. So my first claim is you can compute what is the spectral radius of this new operator, a rho. And I claim that this is, well, first, it's smaller than hg, which remember, sorry, I need to book a log here if I want hg. So this is log 3, and this is larger than hn. So in particular, if you remember what is our goal is to prove that the quotient is amenable when hn equals hg. So reformulated in view of that claim, our goal will be to prove that if the spectral radius of this operator a rho equals 3 here, then the quotient is amenable. So the fact, the upper bound, the fact that the spectral radius is at most 3, it's just, if you look at the definition, or, well, you can look also at the nth power here, you just apply the triangle inequality on the norms, and you will see that you get something which is boils down back to A. So that gives you direct upper estimate for the spectral radius of this new operator. So that one is not very difficult. I want to focus on the lower bound. So to do that, well, basically, we will compute the strategy of the proof is to compute, or at least estimate, the norm, the operator norm of the nth power of rho. Because you may know that the spectral radius of your operator, that the lim sup as n approaches infinity of the nth root of the norm of this operator. So if we can give a lower bound for this operator norm of a rho to the n, then you will get a lower bound for the spectral radius. So let's do that. Oops, I wanted to add a new page. Okay, here I am. So remember, the space we're working in is L1 of S of H. So especially if I want to compute what is the norm, so the L1 norm of a sector vector phi is the sum over all the generators of now the Hilbert norm of phi of x. So that's the norm from my Hilbert space. So what I will do is I will consider a special vector and iterate my operator on a special vector. So what is a special vector? Well, first, I will pick in H, which is, remember, L2 of G mod n, a vector which is the direct function at the identity. So that function from G mod n to R, which is 1 on the identity and 0 everywhere else. And then I will define psi to be so that a function from S to H, so that would be an element in L1 of SH. And this function is a constant function equals to that particular vector psi, which is direct at the identity. Okay, so now let's try to compute what is the nth power, the norm of the nth power of A rho applied to psi. So this is exactly the sum over all x in S of now the Hilbert norm of A rho to the n psi computed at x. And this is definitely larger than if you make the computation the sum over all x of the absolute value of A rho and psi x scalar xi. So what I have written here, so if you think an element in H is a function from G mod n to R, the L2 norm of such a function is always larger than the value it takes at the identity. And this scalar product here is just a fancy way to write the value it takes at the identity. So it's just a very brutal estimate. Nothing fancy here, but that's enough for purpose. So let's now compute this quantity I highlighted here. So this is where the operation will play a role and whether the magic somehow happens. Well, part of the magic happens. So if you compute an rho psi at x scalar xi, so I just unfold the definition of the nth power of my operator A rho. So I look at all the words, reduced words of the form x, y1, yn, which are reduced. So my dynamical system is a counting machine for reduced word. And now I have a scalar product of rho of y1, yn applied to, I apply it to my vector psi computed at the yn, but my vector psi is constant. It's just this xi, which is direct at identity, scalar direct at identity. But what is this quantity? So if you unfold the definition of the Hilbert structure on L2 of G mod n, you'll see that this quantity is 1 if the element y1, yn is in the kernel, because if y1, yn is in the kernel, the rho of that element is the identity. So just taking the scalar product of xi with itself, and you get 1. And if the element is not in the kernel, you get a Dirac and a point which is different from the identity, and the class product is just 0. So what does it mean? It means that, oops, I'm going to, yeah. It means that if you look at this scalar product we just computed, so maybe I should go back to here. So I have a sum of all reduced word, but which is 0 as soon as this stuff is not in n, and 1 otherwise. So I get just all the possible words y1 to yn, so that the first letter is not the inverse of x, and which belongs to the kernel n. So this stuff is just the cardinality of the number of words y1, yn, so reduced word, which are in n, with x, y1 different from 1. But now if I want to compute the norm of a row of C, so the L1 norm in my space of functions, I need to sum this over all possible x. So what I'll get is that this is larger than just the number of reduced words, so which are in the kernel n. So that would be larger than the intersection of n with the ball of radius n in my group G. So now, well, the normal C, I think the normal C in my metric is something like 4. So if you want to estimate the operator norm, that will give you something like this. Operator norm is bigger than 1/4 the cardinality of n intersected with the ball of radius n. But now what is the asymptotic behavior of that quantity? The asymptotic behavior of that quantity is more or less by definition the exponential growth rate of the subgroup n. So that's how you get, after taking the log divided by n and passing to the limit, you get that the spectral radius of this new operator, a rho, is bigger than exponential HCN, which is the end of the proof of my first claim. So if I want to again to summarize, what we did is we had an operator that is only the operator A, which is only counting reduced word, and we have no information where those reduced words are going in the quotient group, G mod n. And then we introduce a new operator, which is basically the same one, but with a twist by the unitary representation in G mod n. So we expect that this representation will help us to track the element in the quotient group. And the first evidence we get of that expectation is that the spectral radius of this new twisted operator is related now to the growth rate of the kernel n. So especially now our goal becomes the following. So we want to prove that if the spectral radius of a rho equals exponential hg, which in our case is just 3, then G mod n is amenable.
A quick question.
Sure.
Did you make an essential use of the hypothesis that the ambient group is free? Yeah.
So here, yeah, maybe I should say a word about that right now. So the assumption I made that the group is free is somehow hidden in that particular dynamical system I chose.
Okay.
Because that one, you know, the fact that the reduced word are the geodesics, that's something which is specific to the free group. If you work, so you can elaborate on this strategy and adapt it for instance, if you study the hyperbolic group endowed with a word metric. But now, so what you will need to count is all the words which are geodesic for that word metric. And these are no more the reduced words. It's a bit more complicated than that. But it turns out that in the case of the hyperbolic group, you can still find a subshift of finite type that will encode exactly those words. And then you can adapt the same kind of strategy for this particular diagonal system, and it makes it easier here to work with the free group, but that's exactly the same thing. And by the way, I forgot to say that, but so this sketch of proof is following argument of Stadelbauer that we have revisited with my co-author Françoise Dalbeau and Andrea Sambucetti. Oops. So this art name behind this strategy.
Thanks.
Other questions? So if not, let me complete the proof. Oops, so I'll add one more slide. So I will do an easier task. So what I said is that we want to understand what's happening when the spectral radius of that operator is 3. So I'm going to be very brutal, and I'll tell you after how to fix that, but I will assume that 3 is an eigenvector, an eigenvalue. Of this operator. So of course that will not be the case. We'll see why, but it makes everything easier to understand, and I think it captures the philosophy. So if 3 is an eigenvalue, it means I have an eigenvector. So there exists a non-zero element. So that's a function from S to H, which is non-zero, such that A rho phi equals 3 phi. And now, well, a second claim, which is not very difficult to see, I'll explain the proof and then I'll tell you why it works in a more general setting, is that if you look at the function from S to H, which sends the generator Sx to the norm of phi of x, so it's a norm that's computed in the Hilbert space H, this is a constant function. Well, why is that? So fix, a generator, you have only 4 of them, so it's fine, it's easy to find one. Fix a generator such that the norm of phi of x naught is maximal. So I'm going to rewrite this eigenvector identity, and the idea is that somehow A and A rho are sort of average operator. So I can write that phi equals 1/3 of A rho phi, which means it's 1/3 of, let me unwrap again the definition, all the xy different from 1 of rho of y phi of y. And what do I mean by averaging operator? So I'm summing over 3 elements and I divide by 3. So I'm doing the average of 3 vectors here. Sorry, that's it's computed at x here. Of x equals. So in particular, if I compute the norm of phi of x naught, I can apply the triangle inequality and I get 1/3, the sum for all xy different from 1. And rho now is a unitary operator. So the norm of rho y phi y is just the norm of phi y. But the norm of phi y is at most the norm of phi at x naught, because I chose x naught to have the maximal norm. So this is always smaller also than phi of x naught. And you have, a sequence of inequality where the extreme terms are the same. So you have equality everywhere. And since you have equality everywhere, you need to have average here, term which have the same norm. So that implies that for all y different from x naught inverse, so here that's x naught, the norm of phi of y equals the norm of phi of x naught. So your function on all but one, maybe, generators, they have the same norm. Well, then you change the x naught for another point, you run again the argument, and you'll get at the end that the norm of phi is constant. So I skipped that part, but you can see if you choose, you apply now this identity to any element y which is different from x naught inverse, you'll get the answer. And here, actually, implicitly, what I used is that the dynamical system I started with, my tool that is coding the geodesic flow, we use the fact that it is topologically transitive, or that it is irreducible, if you prefer that vocabulary. Simplicity is what you use here, nothing else. So how do we exploit now these facts? So here comes my claim 3. That phi, now, which remember is a function from S to H, is constant. So not only if you compute the norm of the function at each point, not only this norm is constant, but the function itself is constant. So why is that? Well, again, we just write what is a rho of phi of x, which is since, well, 1/3. Since phi is an eigenvector, this is also phi of x, and this is 1/3 the sum of all on all x, y different from 1 of rho of y, phi of y. So what do we do here? Well, let's make a picture in H. So let me use some color. Here I have vectors, phi of y, so there are vectors in H, and because of the previous claim, they all have the same norm. So they lie on a certain ball in H. And well, if I apply this unitary operator, that would not change the norm. So I have vector like rho a phi a, for instance, maybe it's here. Here maybe that's rho b phi b, etc. And what I do is I take an average of those three vectors, and I get something which still has the same norm, phi of x. So that's a result of convex Banach spaces. If you take the average of three vectors on a sphere, most of the time the average should be a point inside the sphere, not on the sphere, unless all the points are the same. And this is exactly what's happening here. So the only way you can average vectors which have the same norm and get a vector which still has the same norm if all these terms here and those one are equals. So this relation of being an eigenvector, it translates to the fact that, oops, not what I want. Translates to the fact that phi of x equals rho y phi y for every y different from x inverse. And from that, well, you can get that phi is constant, because here's the observation. So if you take y, x prime two generators, there always exists a certain y, another generator, such that xy is different from y from 1, and x prime y is different from 1. So if you apply the previous identity, you will get that phi of x, on one hand, that's equal to rho of y, phi of y. But that also, if you apply it with x prime, phi of x prime. So you get what I claim is that phi is constant. So it takes the same value on every generator. Okay, so, but not only have we proved that this function is constant, but we proved that the value it takes is invariant under the representation. This is this identity here. So if I copy it below, so another outcome of the proof so the value, let me call it, well, I'll still call it phi, value phi. Well, okay, let me write it like that. The value of phi, so I will still call it phi in the below, satisfy that rho of x phi equals phi for every generator S. And since S is a generating set, that implies that rho of G phi equals phi for every G in the group G. So rho is a vector which is invariant for the representation. Phi is a vector which is invariant for the representation. And not only it is invariant, it is also non-zero, because remember, phi comes from an eigenvector for the operator A rho. So this eigenvector, by definition, is a non-zero vector as well. So now, if you try to understand what is the meaning of that, well, if you remember that
Quick question.
Space, yes?
Is this the only place where you're using that 3 is non-zero?
That's the only place where I'm using that phi is non-zero, yes.
Okay, thank you.
Yes, good question. That's the only place, yes. So now if you take h, you remember h was the square summable function of G mod n. So we have a non-zero function which is invariant for the representation. So such an invariant function has to be the constant function from G mod n to R. So as a function from G mod n to R, phi is constant. And if you think a bit, a constant square summable function, which is non-zero, well, it only exists if G mod n is finite. If G mod n is infinite, there is no way you can find a non-zero constant square summable function. So that will imply that G mod n is finite. So this is where we have been very brutal at the beginning. So what we knew from the assumption Hn equals Hg, the two growth rates are the same. What we knew is that the spectral radius of this twisted operator A rho is 3. And then I made a stronger assumption. I said, okay, let's be crazy. Assume that 3 is actually an eigenvalue of this twisted operator. And if 3 is an eigenvalue of the twisted operator, we were able to produce an invariant vector phi for the representation. And this implied that the quotient is finite. So this was a very brutal assumption to say the twisted operator has an eigenvalue which is 3. But actually now you can go through everything I have done and tweak it a bit to make it work in our context. So more precisely is the way you would work is fix now a set S of G which is finite, and you fix epsilon which is positive, and you may wonder, oh sorry, I don't need the S finite, this is not needed, so I just fix epsilon positive. Fix epsilon positive, and you can say that phi is an epsilon eigenvalue or almost eigenvalue for 3 if, well, the condition is very similar to the one we had for almost invariant vector. So if a rho of phi minus 3 phi is less than epsilon the normal phi. So instead of working with a true eigenvector, you start working with almost eigenvectors. So there is here some operator analysis I don't want to do, but basically you can prove that here, once you have a spectral radius which is 3, you can find almost eigenvectors, not exactly a priori for the eigenvalue 3, but for an eigenvalue which has modulus 3 in the complex plane. But then because you're only somehow working with positive operators, you can always reduce that to having almost eigenvectors for the eigenvalue 3. So here I'm hiding some stuff under the carpet, but they are not that relevant for the rest of my talk. But the idea is that you can somehow reduce your study to, instead of working with true eigenvector, working with almost eigenvectors. And all the arguments I gave you before, saying that the norm of the vector is constant, and then the vector is constant, and then that gives you an invariant vector for the representation, you can sort of quasify all this argument, all this argument. You can add epsilons and subset finite subset everywhere, and the conclusion was a constant, but the conclusion you will get is that the representation rho almost has eigenvectors. Maybe I should okay, sorry, I should write more precisely what my assumption is. I select, yeah. Let me be more precise what I want to mean or to say. So what I want to say is that if, well, oops, it's not what I want. Yeah, so if you assume that for every epsilon, a rho has epsilon eigenvector for the eigenvalue 3, by the way, here is not value, it's vector. So if your operator has, almost eigenvectors, you can find something which is as close as possible to an eigenvectors, then you will get, by epsilonifying all the arguments, that the representation here has almost has eigenvectors as well. And saying that the regular representation has almost eigenvectors, this is my definition of amenability. So it means that the quotient G mod n is amenable, which is the conclusion I wanted. So yeah, just a few words about the last step. So you can also, if you don't want to carry all those epsilon, etc., you can also have some nice limit arguments where you will consider ultra limits of certain representations and certain operators, and you can reduce everything to the case of having a true eigenfunction. I will not detail that yet for because we will come back on it probably on Wednesday. So, but what I want to really stress, well, there are two things I want to stress. So first, if you know the proof, well, there are several of them, but one proof of Keston criterions for amenability is exactly the one I gave you. I think that's a proof which is due today originally. It's not Keston's original proof, but the idea that you look at the Markov operator of your random walk, and you say that if the Markov operator almost has invariant, an invariant function, then the representation almost have invariant vector, and therefore the quotient is amenable. That's the exact same proof that I run here, but instead of using the random walk as a dynamical system, I use the geodesic flow, basically, which here, because we are using only the free group, is just considering reduced words, so that make our lives easy. But you can sort of manage the same kind of thing in a more general setting. So the second important point I want to stress is this twisting strategy. So somehow we have one operator which counts reduced word, and we have the twisted operator which not only count the words but follow these words in the quotient group. And there is a comparison between the spectral radius of those two operators, and when those spectral radius are the same, we are able to prove that the quotient is amenable. So that's a very nice strategy. It has a drawback, though, a huge one. If you're working in the manifold, well, you can, or if you're working with the word metric of a hyperbolic group, for instance, you can run this strategy because somehow there is a tricky way to encode your geodesic flow, which is a dynamical system which is relevant here. You can encode the geodesic flow as a subsheet of finite type. So that's graph. You have a more complicated graph, but basically that will work in the same way. If you move to a general cat-1 space or hyperbolic space, and if your action is normal, proper, compact, or you can have some all nasty stuff that's happening, this strategy to encode the flow as a subsheet of finite type will fail. So you're doomed here. You cannot use that kind of thing. And this is where we will adopt a different method. The idea that we will transfer all the thing we have done in terms of operators using measure on the boundary of the space we are acting on. So we consider group G acting on space X. We consider the boundary of the space, and we have a certain measure of the boundary that will sort of play the role of the operator. So there will be a real value measure, which are now well understood, called Patterson-Sullivan measure, which will play the role somehow of the usual transfer operator, which is here my matrix A, which is still on the board. So this one is pretty easy, just a real value measure. I'll go through tomorrow through this construction if you don't know it, but nothing very difficult here. Now it's very well digested. But now we need something that will play the role of the twisted operator. And so the natural thing to do will be to build a measure with a twist by representation, which means, so I'm kind of spoiling the rest of this lecture, but I will give you where we are going. We are going to consider a measure that takes value not in the real numbers, but in the binary space of operators. So that can be frightening at first. You'll see you just have to take a deep breath. Most of the stuff is formal. I'll give you another way to think of it to put your mind at ease if you're not familiar with that. But one, you have taken that psychological step to say, okay, why not considering measures which are twisted and takes value in the binary space? Once you have taken that psychological step, you see that many of the arguments are run on the level of operators. They have an analog in at the level of measures, and that gives, I think, a strategy which is an improve, which is very nice to tackle those kind of results of amenability. So yeah, I'm almost out of time. I think I stop talking here, but if you have any questions, I'm happy to answer.
Yeah, thanks a lot, Remi. Thanks a lot for this beautiful introduction to a beautiful subject. So yeah, any questions? Yeah, so yeah, I have, yeah, any questions?
Sure.
Yeah, okay, so I have one question. So one thing is you've used here the normality of n, but if you take care of, say, left and right actions, does the same proof essentially generalize to, say, coamminability of n in the free group?
Yeah, exactly. Here's the same proof will normalize. So I will introduce later coamminability. I did not want to introduce everything, all the words and all the weird thing at the same time, but I will introduce coamminability maybe tomorrow on Wednesday. And in that setting, the exact same proof work for any subgroup. It doesn't have to be a normal one.
Okay, thank you. Thank you.
Yeah, you just have to be careful about the left and the right, and maybe I made some mistake with some inverse in my formulas because of that, but yeah.
All right, so let's thank Remi for this wonderful talk and look forward to hearing more about the same.